So we're talking about conservation of angular momentum. We're talking about it on a more macroscopic scale. So we're talking about rigidly rotating bodies. And we determined that the total angular momentum of that system before whatever the event or the collision is has to be equal to the total angular momentum of the system after the collision. So we're actually going to try one that's a little bit more like a collision today. So let's do page 324, number 55. And I am really hoping that we're going to finish this today and y'all can start reading chapter 12 for, which is my favorite chapter. All right, somebody read this for us. Gianni, help me out. Vinyl. A wad. Right, and I would say a wad of wet putty. Is that what comes next or no? Okay. Putty, does everybody know what putty is? It's like the Play-Doh that I've been playing with in calculus. So it's real squishy and you put it into holes to block up the holes and it'll dry hard. Okay, that's what putty is. So it's like clay. All right. So I've got a record. Everybody know what a record is? It's like a CD, but it's a little bit bigger and it's made out of something else. Okay. So I have this record and it has some initial rotational inertia that I happen to know. Okay. And so I know that the mass of the record is what, 0.10 kilograms. The radius of the record is 0.10 meters. I of the record is what, 5.0 times 10 to the negative fourth kilogram meters squared, and my omega initial is 4.7 radians per second. Yes? All the info that we got? Okay. And then what happens? Okay, and then the putty falls. And where does the putty land? Near the edge. So here's my mass of putty. And the mass of my putty is 0.020 kilograms, right? Okay. And what's going to happen? What's going to happen to the record? What's going to happen to the system? It's going to slow down. Okay. So there's going to be some new omega. If angular momentum is conserved, if I've added more mass to the system, then the velocity has to change. But wait a minute. Can I add mass to a system and conserve momentum? No. So what do I have to add to my initial picture here? No. If that's my system after, what does my system before have to be? How many objects are in my system afterwards? How many objects have to be in my system before? I have to include the putty, okay? Even though it's just sitting up there, not doing anything, okay? But I can't add or subtract mass from my system. Momentum is conserved for a closed, isolated system. So does my putty have momentum, angular momentum here? No, it's just sitting there. It has no velocity, okay? But it has the same angular, well, I'm sorry, that's not true. It has the same omega as the disk afterwards, okay? So this is going to be my initial situation. This is going to be my final situation. And I'm going to say that my angular momenta before and after are equal. So I've got Li is equal to Lf. What's my formula for angular momentum in this situation? I omega, okay? But remember that I've got I omega for the record, and I have I omega for the putty. And I'm going to have I omega for the record final, and I omega for the putty final. It is part of my system, though. I'm going to make it go to 0, but the putty is part of my system and should be listed there. Okay. Sure. It can go, I mean, I wouldn't erase it, but it can go to 0 because it's not moving in my system. Okay. So I've got, and really well, it doesn't matter. The rotational inertia of the record itself doesn't change. Okay. Times omega Ri. And I can really pull out both of those omegas and make it an omega F, because the putty and the record are going to be turning at the same rate. So that's going to give me I record final, and just remember that those two are going to be equal because the record itself doesn't change. But if my putty is pretty small and pretty compact, how do I write its rotational inertia? Yeah, it does a lot. mr squared. So it's going to be the mass of the putty times its distance from the rotational axis squared. I didn't say it had negligible mass. I said it was compact, which is the whole idea. If it's compact, if it's all small and together, then I don't really have to worry about different parts of it having a different velocity or anything. Okay. So my omega final is going to be IR omega initial, IRF plus MPR squared. Nope, this is it. So then my I was what, 5, what was it? 5 times 10 to the negative 4th. So I got 5.0 times 10 to the negative 4th kilograms meters squared times 4.7 radians per second divided by that 5.0 times 10 to the negative 4th kilograms meters squared. My putty was 0.020 kilograms, and the radius of my disc was 0.1 meters squared, or 0.1 meters. And so what do we get for omega F? What'd we get? What'd we get? What'd you get, Priya? Good. Is that what you got, Sari? No? No. You also got 3.4. Make sure you get all your parentheses in the right spot. And that you square the things that should be squared. Okay. All right, other people get it? All right, we'll let Sari figure it out. And after all, it's just the math. If you got it all right, then I'm not going to worry about the calculator part. So let's try page 324, number 58, because this one's, again, a little different. So if somebody would read it for us, please. So thank you. Okay, so can we visualize what's happening here? I've got my platform. Excuse me, I seem to be not lining up here. That's bothering me. So we've got the platform. She starts on the outside. And she walks to the inside. So what's changing? Her inertia is changing. Is it getting bigger or smaller? So what, there, I feel better about that. What should happen? No, I feel terrible about that though, because I seem to be, oh, there's my person. She has a lot of red hair. Looks like my friend Marsha. Okay, so she's out here and she's going to walk in. All right. Her rotational inertia is going to get smaller, so what's going to happen to the disc? Why is it going to speed up? Okay. So her R here, our student is going to be what when she's out at the edge of the disc? Two meters. And her radius here after she walks is going to be what? 0.5 meters. Okay. So I have my initial situation and my final situation. And I got a whole bunch of stuff that I know, but I'm not going to write it all down because I'm not. So if this is a closed system, and it is, then that initial momentum has to be equal to the final momentum. And again, what's the equation that I'm going to use since these are big macroscopic rigidly rotating objects? What's the formula I use? I omega. Okay, so I'm going to have I disk initial times omega initial, since everything's rotating at the same rate, plus I student initial omega initial. And that's going to be equal to, in fact, I'm just going to make it be I disk, because the disk itself doesn't change. I disk times omega final plus I student final times omega final. have all those things, so that's a number. But I might. So I could factor out omega final from the other side and add it to, and all of this will stay the same. There's something wrong with the reckoning here. Yep. Okay, so again, compared to the size of the disk, what can you tell me about the student? She's fairly compact. Compact is a good word. Well, it is. Okay, so I, student initial, what am I going to use for that when I have a compact object? MR squared. Okay, and then I, student final, is going to be M I final squared. So once again, tell me what the answer is. It's not quite what I get. Yeah, but 2.57 doesn't round at 2.8. No, Zoe's got it with 2.57. Again, you just have to make sure that you get all your parentheses in the right spots. And I am taking shortcuts today. I am not writing down all of my notes. You still need to do that. Okay. I just want to make sure we get through everything we got to get through. Rewriting the problem took more space than the actual problem. We're good. Yeah, I know, but I want to make sure we get through it. If I could, I'd go back at 11:30 and rewrite out all the notes, but that wouldn't make sense. All right, we good? We got it? All right. So, page 324, number 53. Okay, go. Do what you got to do. Make sure you watch the last problem, though, because it's very different than what we've done so far. All right, somebody read for us, please. So let's visualize this. Here's my rod, okay, and it has an axis of rotation in the middle here. Okay, and it's here on the table, and it can spin this way on the table. Okay, so it's sitting here. Something's going to come in from this direction and hit it. What's going to happen? It's going to start spinning, right? And that thing, because it's a rod and it has some thickness, that thing is going to get stuck in it and make this whole system start to spin. Okay? So you with me? Okay, because we got to make sure we can visualize it. So the bullet comes in. Kinda. Also, there's probably like things in pinball that do that too, but okay. And it comes in at a 60-degree angle, right? And this distance is what, 0.25 meters? Because the length of the whole rod is 0.5 meters. Okay. So after my projectile comes in and gets lodged in the rod, what kind of momentum do I have? Yeah, after it comes in, my bullet comes in, it gets lodged in there. What kind of momentum do I have? Angular momentum, rotational momentum. What kind of momentum do I have before when only the bullet is moving? Linear. Okay, so this is kind of weird because I've got a linear momentum that turns into an angular momentum. And I can't necessarily say that those two things are equal to each other. Because even if you think about the equation, they're not. They don't even have the same units. Okay? But I'm very obviously going to have angular momentum afterwards. So what I do is I pretend that my bullet, holy cow, I have no idea what happened there, is I pretend that my bullet has angular momentum around the rod's axis of rotation. Immediately before the collision. Yes, we will. Okay. And really, that's a very important thing, is that anything can have angular momentum, any moving thing can have angular momentum around any axis. So I could walk in a perfectly straight line and have a different angular momentum as if each of you were my axis of rotation. Yes, because it will change. Because every time I take a step, I get farther away from Elisa, but closer to Zoe and Maddie. Okay, and so my R changes, even if my velocity is the same. So that's why I'm very particularly saying here that I'm talking about the bullet immediately before the collision, so that I can just say that the R value is going to be that 0.25 meters. Okay. So again, I have that my initial momentum is equal to my final momentum. And my rod can have an initial momentum, and my bullet has an initial momentum. And they also have final momenta too. No, what are they going to have the same though, maybe? Or what will they have the same? Not inertia. Yeah, they'll have the same angular speed after the collision, and we can combine that after we write this out. Okay, but what about the rod's initial angular momentum? It's 0. Okay, so that's going to go away. So for the initial momentum of the bullet, I'm going to have I bullet times omega I. And then afterwards, I'm going to have I rod plus I bullet times omega final. Right, so let's go up here for a minute. What's I bullet going to be? Okay, so it's going to be mr squared because it's this compact mass that has a very small radius with respect to the rod. Yes, in this case, r will be 0.25 meters because that's going to be the distance between where the bullet is and where the axis of rotation is, because we're talking about that instant right before the collision. Well, I do have to talk about what I'm going to do about VI, but remember that VI is going at that angle. So maybe I need to look at the angular momentum a different way. What might be another way I could look at that angular momentum? It wouldn't be angular momentum, so it wouldn't be d theta dt. But no, that would be the derivative of the angular momentum. That's not what I... No. Yeah, okay, this could be my angular momentum is r cross p, right? And I've got this tiny little point source. I can factor out my m, and I get r cross v. And as Priya said, r cross v is rv sine phi. Which is what this is what I'm looking for, right? I know what phi is. What's phi? 60 degrees. I figured out my r, and I know what my m is. Yes? Okay, so then this is going to be equal to I rod plus I bullet omega f. Okay, so I need my I for my rod, though. No. Thin rod. Yep. Plus little m r squared, because we said that's what the rotational inertia for the bullet will be. you want to solve for V, right? So that, honestly, even if you don't write down the numbers after this step, if you have it this way when you're plugging it into your calculator, I think you'll have a better shot of getting it right than trying to plug all the numbers in and do it in your head. And let's see. I am not going to answer that question because you should know how to convert grams to kilograms, even if you have to write it out. Make sure you're in degree mode.